Welcome to the problem-solving portion of this topic. I have a small update to the table of contents. Basically, I'm adding one other type of problem that we're going to work through. So those are going to be Bohr model calculations, and then we'll still look at the orbital diagrams. So let's go ahead and get started. Here's the first problem that we're going to do. This is from Chapter 7, number 63, Part A. Question asks us to calculate the wavelength of light emitted when each of the following transitions occur in the hydrogen atom. We're just going to be looking at one transition, okay? And then once you do that, what type of electromagnetic radiation is emitted in each transition? Okay, so we're going to calculate the wavelength of light emitted when an electron goes from n equals 3 to n equals 2. And based on that wavelength, we're going to try to deduce what type of electromagnetic radiation that is. So let's go over to the document camera. Once again, this is Chapter 7, number 63, Part A. And we're going to be going from n equals 3 to n equals 2. And what that means is that we have an electron going from n equals 3 to n equals 2. This problem is in a section in the book titled like Bohr model problems. Okay, so this is using the assumptions of the Bohr model, and I ask you to do a few problems from that section. So what you'll see on that page in the book and throughout the chapter, specifically in the spaces that are talking about Bohr model, is this type of diagram. Okay, so it's a diagram that just sort of it's actually more of a graph, to be honest with you. That looks something like this. I'll try to draw it as best I can here. And on this left side, this is energy increasing, and these different lines here represent the different energy levels in the Bohr model for an atom. So what we're tasked to do is to calculate the wavelength of light emitted when this transition occurs, n equals 3 to n equals 2. Okay? So how on earth do we do that? Well, let me go back to the slides. If I go way back through the slides, we get to the first slide on the Bohr model, okay? And I referenced this equation, okay? The energy levels can be expressed according to an equation of Bohr's derivation. I said that we may come back to that later. Well, here we are, okay? I'm going to copy down that equation onto the document, or onto my paper here, and we're going to be using that, all right? So the equation was E is equal to negative 2.178 times 10 to the negative 18th joules, and then there's this factor at the end, z squared over n squared. Okay. It's kind of weird that the unit is like in between this number and this factor here, which is going to end up being a number as well. Don't worry too much about that. In fact, I may have screwed... No, that's what it... Well, I'm not sure why it looks like that exactly, but basically we're going to be taking whatever this value comes out to be, multiplying it by this negative number here, and that's going to be our energy. Okay. Now the thing is, this is just going to be our energy for one of the levels. What we're going to need to do is calculate the energy at this level at n equals 3, the energy at this level at n equals 2, and find the difference between those two energy levels. Okay, we can then use that energy to calculate the wavelength of light that's emitted, and that's what the first part of the problem asks us to do. Okay, so let's take one more look at this equation here, make sure we have everything we need. We're trying to solve for the energy. We know what n is. It's going to be 3 and 2 for our two different calculations. What is z? Okay, z is nuclear charge, okay? In chemistry, I believe that's the only thing Z is ever really used for, that I can think of at least. It means nuclear charge. What that means is the number of protons, okay? It's like the magnitude of positive charge in the nucleus of an atom. So because the Bohr model really only applies to hydrogen, and all these questions about the Bohr model are asking you to assume that it's hydrogen, Z is just going to be equal to 1, okay? So I'm just going to go ahead and scribble that in here, right? And if it's Z squared, then 1 squared would also be 1, okay? So this is really my equation here. Okay, so let's find the energy at n equals 3. This would be equal to negative 2.178 times 10 to the negative 18. I'll save the joules part for here in just a minute. Okay, so it's 1 over 3 squared, right? N squared, which is 9. Okay, that'll be in joules. Let's go ahead and figure out what that is. Now you're not going to be able to see. Well, you may be able to see the screen on my calculator here. It's a bit dark. It's not lit up like my phone, but I'm going to start using my fancy calculator for these types of calculations. All right, negative 2.178 times 10 to the negative 18. Divide that by 9. Okay. The answer I get is negative 2.42 times 10 to the negative 19. Okay. The more negative this exponent, the smaller this is actually getting, right? That makes sense because it's we're dividing by 9. Okay. Let me put that in a little box. That's the energy at n equals 3. Let's also calculate the energy at n equals 2. Okay, same thing. Negative 2.178 times 10 to the negative 18, 1 over 4, right? Because if n equals 2, then that's just 1 over 4 joules. Let me add that unit here. Okay. So I'm just dividing this number by 4. I'll do that on my calculator really quickly. Negative 2.178 times 10 to the negative 18 divided by 4. Get negative 5.445 times 10 to the negative 19 joules. I'm not going to be paying attention to significant figures for the moment. We got more important things to deal with than trying to keep track of sig figs. So, all right, that's the energy at n equals 2. Okay. So now we need to find the difference between these. It doesn't really matter which way you subtract, okay? There is a proper way to subtract, like one minus the other versus the other way around, but what we're really interested here is just the raw difference, okay? So we're essentially going to be taking the absolute value of the subtraction here, okay? So don't get hung up on, which of these goes first. I guess technically we could do like the n equals 2 minus the n equals 3. That seems to make sense to me in my brain. But at the end, we're just going to be taking the absolute value anyways, so it doesn't really matter. So let's just go ahead and do that. Let's do the energy at n minus 2 minus the energy at n equals 3, absolute value of that. That's going to be negative 5.445 times 10 to the negative 19 joules minus a negative 2.42 times 10 to the negative 19 joules. Okay. Great thing about a fancy calculator like I have is that these values are saved in the calculator, so I can just press 1 and then subtract the other. So I quickly end up with this answer here, negative, and once again, right, it's a negative, but we're going to be taking the absolute value. Okay, so I'm going to hack off the negative right there. this is just going to be 3.025 times 10 to the negative 19 joules. Okay, so that's the delta E, okay, or change in energy, all right? We'll say from 3 to 2. I realized I've been writing that last part there below where you can see it on the camera, but it's not that hard, okay, so you guys should be fine. All right, so this is just some subtraction, right? So there's the delta E. This is the change in energy, okay? The question asks us to find the wavelength, okay? This is where, I'm going to pull you back to the slides. On the previous slide here, I have an equation, okay? Let me go ahead and write this down on my paper. This equation tells us that the change in energy is equal to h nu, or h, this little letter here, it means frequency, and frequency is just equal to the speed of light over wavelength. Okay, so this is also equal to this. Okay, and we are concerned with what the wavelength is. Okay, so we have a delta E, h is a constant, c is a constant, and the wavelength is what we're solving for. Okay, let's figure out what those constants are. This is called Planck's constant, h. I believe I do mention that during the notes slide. You can find it in your book somewhere. I'm just going to Google it because I don't have my book open at the moment. Okay, Planck's constant is approximately equal to 6.626 times 10 to the negative 34. I believe that's in units of joule seconds. Yes. Joule seconds. So joules times seconds. C, like I said before, is the speed of light. This is approximately equal to 3.00 times 10 to the 8th meters per second. Okay. It's totally fine if we get a wavelength that is in meters. Okay, so we don't have to do anything with this just yet. Okay, so let's set up the equation and plug in our values. Okay, so our delta E was 3.025 times 10 to the negative 19 joules. This is equal to, we're not really focusing on this part of the equation right now, we're looking at the ends. This is equal to H, 6.626 times 10 to the negative 34 joule seconds, times C, 3.00 times 10 to the 8th meters per second. Notice how I have seconds in the numerator here and then seconds in the denominator here. Those seconds are going to cancel out, and this is over the wavelength. Okay, so my variable that I'm solving for is in the denominator. I'm not going to go through the algebra here. Basically what you end up doing is just switching these two terms. Okay, that's what the algebra tells you to do. So it'll be lambda is equal to this h times c over the delta E. Okay, so my lambda is 6.626 times 10 to the negative 34 joule seconds times 3.00 times 10 to the 8th meters per second. Once again, those seconds are going to cancel, and this is over my energy value. I think I have a little bit more space here. 3.025 times 10 to the negative 19 joules. Check this out. Joules in the numerator, joules in the denominator. Those are going to cancel. All I'm going to be left with is meters, which is good because that would be a length, right? A wavelength. This is then equal to, okay, let me punch all those values into my calculator. It's going to take me just a moment. Okay. 6.57 and some change times 10 to the negative 7 meters. Okay. Now, wavelengths of light are usually given in nanometers. Okay. So what I'm going to do is I'm going to convert this quickly to nanometers. Okay. There are 10 to the 9th nanometers in 1 meter. Okay. So my final answer, right, this is going to cancel out meters, is going to be this answer times 10 to the 9th, which is 657. That's the wavelength of light. Okay? And it asked us, the final part of the question was, what type of electromagnetic radiation is this? Well, check this out. You see this value right here? 656 nanometers. That's pretty darn close, okay? So this would be visible light radiation of the orange variety, right? The reason it asked that question is because technically these energies, or these wavelengths rather, of the energy that's emitted could potentially be off of the scale here. They could be non-visible radiation. If it's in this direction, off the scale to the left, you can see here, right, off the scale to the left would be beyond violet or ultraviolet, right, assuming it's not too far off the scale. And then on the opposite end, going past red, then you get into the infrared. You can just Google a diagram of the electromagnetic spectrum, and it will show you all of the ranges of the different types of electromagnetic radiation. Okay, well, that was quite a doozy. Those calculations aren't too bad, though, because really all you're doing is just plugging in values of n and punching things into your calculator. So there are some questions that do ask about using that same equation with the Bohr model and different transitions. Okay, let's take a look at some electron orbital problems. Okay, so next thing we're going to look at, draw atomic orbital diagrams representing the ground state electron configuration for each of the following elements: carbon and chlorine. How many unpaired electrons are present in each element? Okay, so carbon and chlorine. Get my paper here in a good position. All right, so let's start with carbon. Symbol C. Atomic number, or Z, right, nuclear charge, equal to 6. Okay, I'm going to start using that actually a little bit more often just so we get used to it. Okay, Z is just nuclear charge, aka atomic number. Okay, it's number of protons. So we're going to assume that we have neutral atoms. I don't believe the problem tells us that, but we're going to assume that these are neutral atoms. So if my atomic number or my nuclear charge is 6, then we're just going to assume that we also have 6 electrons. Okay, and we need to draw the orbital diagram to illustrate the electron configuration. Well, the first thing we should do is we should just come up with the standard notation electron configuration. That's going to help us when we draw the boxes. Okay, so this is what most of you should have been able to do last year, and hopefully if you were having some trouble with that during the videos earlier, you looked at the extra resources that I provided at that time. The electron configuration for carbon is this: 1s2, 2s2, 2p2, right? 2 plus 2 plus 2 is a total of 6 electrons there, okay? So, on to the orbital drawing, okay? The way this works is we have a box for the 1s orbital, a box for the 2s orbital, and then the 2p orbital really contains space for 6 electrons, right? And as I explained in the notes portion of the video, the p orbitals actually are made up of 3 different orientations of orbitals. Okay, so there's 3 different boxes. That's what That's why p orbitals can in total hold up to 6 electrons. Okay, so these all represent the 2p orbitals together. Okay, and then the way that we do this is we fill in these boxes with arrows, starting with the lowest energy orbital, which is the 1s, and you're going to do like an up arrow and a down arrow, right? By the way, that's a common way of doing it. Instead of having like both heads of the arrow there, you can just do one. It's a little bit easier on the hands, and honestly, I think it looks kind of neat. So there we go. We need to make sure that the arrows are in opposite directions, so as to indicate that our electrons have opposite spins. That's part of what the Pauli exclusion principle says, that your electrons that are in the same orbital have to have opposite spins. And the reason that they both go into the 1s orbital instead of going any further, once again, we're going to try to fill in the lower energy orbitals first. Okay, so that takes care of 2, or this portion. Then I get my third and my fourth electron in the 2s orbital. Okay, so now we're at 4. 2 more electrons to go. Based on our standard notation electron configuration, they're both going to be in the 2p orbital, but we've got different positions here. Okay, so what I could do is this, right? Or, okay, and this is completely valid, okay, or what I could do is I could do this. I could do down arrows first, okay? It doesn't really matter, okay? What is important is that I have these 2 electrons in separate spots, okay? This box, and this box, they're all like equal energy, okay? So the 1s orbital is definitely lower energy than the 2s orbital, but all 3 of these are like equivalent with each other, okay? I believe there's a term for that called a degeneracy. All 3 of these orbitals are degenerate, meaning they are of the same energy, okay, I believe. I'll get some clarity on that for you if that is not the case. So the one rule that I did mention in the video that does apply here, though, is that we do have to spread these out, okay? We can't put this second electron in the same box with that first one, okay? We're going to spread them out, okay? And the reason for that is electrons are negatively charged. They prefer to spread out, right? If they're all negatively charged, they are all repelling away from each other. So in 3-dimensional space, the electrons are going to try to move or be as far apart from each other as possible. And so what we end up with is those electrons in different places. Let's say I was working with nitrogen, right? 1 more electron, it would go here. And then when I move on to oxygen with 1 more electron, then it would be able to go into this box here as a down arrow. Okay? All right. The final question on that slide asked how many unpaired electrons are present in each element? 2. Okay? So carbon has 2 unpaired electrons that are in that 2p orbital. All right, let's tackle the next element. It was chlorine, atomic number 17, and like I mentioned before, we're just going to assume that these are neutral atoms, so we're going to assume that it has 17 electrons as well. Okay, we need the standard notation electron configuration. It's 1s2, 2s2, 2p6, 3s2, 3p5. Okay, that gives me a total of 17 electrons. Let me go ahead and draw my orbital boxes. Okay, you might be thinking to yourself, how neatly do I have to draw these? Well, you know, I'm trying to draw them fairly neat here because I'm doing this for like an explanatory video. If yours aren't quite as neat as this, then I completely understand. Just be aware that I need to be able to see what's in your boxes, okay? Like I need to be able to see the difference between an up arrow and a down arrow whenever you draw yours, okay? Believe I'm just about done. There we go. Let me label these, okay, according to what they actually represent. This is the 1s, 2s, 2p, 3s, 3p, and I'll go ahead and start filling these in. So there's 2, 4. The order at which I fill these in, watch this. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now I'm at a total of, what is this, 12? Yeah, 2, 4, 10, 12. Okay, 5 electrons into the 3p. I'm going to do these 3 first with their parallel spin, and then I get the 4th and the 5th one there. Okay, so how many electrons are unpaired? Just the 1. Okay, so this part really shouldn't be that bad. You know, there was a lot of concept that I talked about in the first video. If you were getting a little lost during that, hopefully this right here doesn't seem that bad compared to some of that stuff. Okay, and let's get to the last problem, which is a problem from the book. This is also in Chapter 7, number 97, Part C. Given the valence electron orbital level diagram and the description, identify the element or ion. Okay, so I'm going to not pull this up on paper. I'm just going to talk about it. So we're looking at Part C here. First thing I want you to notice, we only have 4s and 4p. When you see that, what you can assume, unless it says otherwise, is that the remainder, or actually the first part of the orbital diagram is there. It's just not shown to like save some space. Okay, the part that they're showing us here is the important part. Okay. All right, so we have all this other stuff over here, like the 1s, 2s, all of that. What's important apparently is right here, 4s and 4p, and it tells us that this is a ground state ion with a charge of -1. What's an ion? An ion is an atom that has a different number of protons and electrons. Okay? So remember, the number of protons identifies which element it is. The number of electrons can be different. Okay? So, for example, an atom of carbon could have 6, 7, or 8 electrons. It could have more, it could have less. Okay? So, what this says is that this is an ion that has a charge of -1. What that means, because electrons are negatively charged, is that whatever atom this is, whatever element this is, there's one more electron than proton. Okay? So, with that in mind, let's keep taking a look here. So, I have a full 4s orbital and like a nearly full 4p orbital. But I don't know how many total electrons this would be. Well, let's back things up a little bit. So I talked a little bit about noble gas notation, okay? And I showed you this diagonal rule thing. Let's look at where our orbital diagram starts again. Starts at 4s, and I told you before that unless they state otherwise, you can assume that the part that would be off to the left here, that would be full. So let's see if we can actually add up the total number of arrows that we would have over here on the left-hand side. So 4s is where we start. So what comes immediately before 4s? This is where you can use this diagonal chart, okay? So the electrons get filled in according to this chart in the direction of the arrows, okay? So if 4s is what we have, and that's the first thing we see, the orbital that comes immediately before that would be 3p. And then before that would be 3s, and then 2p. We're kind of going backwards here, then 2s, and then 1s. So these 5 orbitals here, right? This is what we start with, so go backwards here, 3p and onwards. These 5 orbitals here, we can assume those to be full, and that's what we can't see. So let's add up the total number of electrons here. 2, 4, 6, plus another 6, plus another 6. So that would be 12 and 18. So there's 18 electrons that are sort of not written here, but assumed to be there. 18. Okay, well then this is 19 and 20, 21, 22, 23, 24, 25. Okay, so 25 electrons. But remember, this is a ground state ion with a charge of -1. As we previously discussed, this -1 means that the overall atom has a -1 charge, which means it has one more electron than protons. Okay, So if this has, what did I say, 25, right? If this has 25 electrons, that means it must have 24 protons, okay? If I consult my periodic table, element number 24 is chromium, okay? So this is the element chromium. It's an ion of chromium with a -1 charge, okay? The way that I would draw that, I'll show you this just briefly. Let me not waste a full piece of paper on this. The way that I would draw that would be like this: Cr, -1. That would be sort of the symbol or the way to notate that this is a chromium ion with a charge of -1. Okay. I believe that after watching the videos and taking a look at these example problems, you should be able to handle all the problems that I've assigned you for this problem set. Just as a note, because this topic was so lengthy, we're going to be pretty much spending the entirety of Wednesday like working on the problem set. Okay, so I'm probably not going to have any sort of like challenging problems for you on Wednesday. We're going to sort of work on the problems on Tuesday, answering some questions that you guys might have, and then we're also going to work on the problems in class on Wednesday on C-Day as well. Okay, and I'll give you guys plenty of time to be able to ask me questions. We may work on some problems together in a more cooperative fashion. All right. Okay, thanks a lot for watching, and I will see you on Tuesday.